Today's talk is about service chaining with hardware acceleration in virtualized environment. Before we talk, some credits to the main contributors. The solution is simple, but it was hard to get there, so thank for all those guys for helping. Let's skip the agenda and jump in. Okay, so in the recent years, or let's say the two last decades, services moved into the cloud. Okay, and the cloud, in order to do that, it became virtualized. Okay, you want to utilize your hardware, save cost, better memory, better network, better everything. It's more dynamic, and it's you need a lot of work to do in order to deploy and to reconnect your network. Side by side with that, there is also what we call VNF. VNF is network function. This is more belongs to the infrastructure of the network, and it's like a gateway or a firewall or a router, things like that. And they had like two steps in the evolution. First step was not working anymore on a dedicated hardware. You just take off-the-shelf hardware with standard NICs, DPDK, and you have this appliance now. And the second one is what they are doing now, which is cloud native. It means that they can run fully virtualized on the cloud. And this is the focus, how we accelerate it. Together with the virtualization came another thing, which is software-defined network. It means that we can we split the network into a centralized controller. The most famous open source is OVN or Oven, and also the data plane, which is separated, and in the community it's used OVS. And there's also standard to configure your network, which is OpenFlow. And this gives a lot of flexibility and a very fast phase in developing new feature and automation. And this is what most CSPs are doing. Some of them are using open source, but others have the exact same architecture, but they are not using OpenFlow. They have their own proprietary API. Okay, so we have a lot of benefits of doing SDN. But what happened is some of the functionality moved from the switches into the host. You now need to move packets inside the host, and you need to put CPUs in order to do that. Until recently, it was, let's say, okay. But now, let's say 5 years ago, it was 10 gig, but today, or maybe 25 gig. But today, CSPs are putting 200 gig NICs on the host. And in order to move 200 gig, what's on a regular workload is about 30 million packets per second. If you're looking on let's say, implementation of switches, virtual switches, the range that of packets per second they can do is about 500,000 to 1.5 million. Sometimes if you do something more optimized, you can do more, but then you lose the flexibility. And it means you need to put like 20 cores or 30 cores on the host, just moving packets. And this is not going to be better, it's going to be worse because bandwidth is increasing. We have now 400 gig and 800 gig for AI workloads. In AI workloads, the packet size is bigger, but usually you can have 8 NICs on the same host. Okay, so in order to maintain the requirement, CPU can no longer do it in software. Okay, we need hardware assistance. So this is example just like the previous talk. You have, in DPDK, you have RTE flow, which you can define pattern and actions. And when the packet is going through the hardware, it will match and do the actions according to the user configuration. It's usually split into two. One is the control path, which means that if the packets that you don't know what to do with, you send it to the software doing processing. For example, if it's Suricata, it's do packet inspection or something. If it's OVS, it decides according to OpenFlow what to do in order to direct the packet to the right place. And then you can configure the hardware And from that point, all the logical flow, all the following packets will go through the same match and action pattern, and you can get a very high rate. Okay, so this is already implemented in many places. In the obvious, which we couldn't push, I see the obvious guys there, but we have our own obvious implementation that we can get 30 million packets per second with a high scale. Okay, and this is what we already have. I'm taking a firewall as an example, but now customers are coming and they're saying, I want to run also a service. Okay, I have the switch, everything running perfect, 30 million, I'm happy. But now my customers wants to add another services, like firewall. This is one of them. So how it works today they're only using it for the north-south traffic, like going out of the cloud and going back. But now they want it on a east-west. So what it means today, they need to send a packet to the firewall. The firewall is an appliance in their cloud. They need to send the packet to the firewall, get the packet back from the firewall, and then send it again. So they get only a third of the bandwidth they have. Okay, they're wasting 2/3 of the bandwidth. And of course, the scalability issues and load balancing, you need to assign each firewall, each appliance to some host, and it's very difficult to maintain. Okay, so the obvious solution is put the firewall inside the host. Okay, you have a switch, the switch is directing the packet, and now you add just another connection. Instead of sending the packet to the firewall outside, you're sending it to a VM internal to the host with the firewall. The firewall will process the packet, will send it back to the switch, and then you do the other switching and send the packet to the workload, and the other way around. Okay, so this solves the, let's say, the scalability issues and the wire performance issues. But the problem is that we break the hardware acceleration now. Okay, it's no longer fully hardware accelerated because you accelerate from the wire to the firewall, from the firewall to the switch, from the switch to the workload. This is fully accelerated. But the firewall itself, it's now a software only, and we are back to the problem that we cannot provide enough performance to the customers, or we need to put too much cores, and then it's not effective. Back in the DPDK summit, I think Ori Kam did it, right? It was yours, huh? We introduced hairpin. What is a hairpin? Another problem with this topology that I didn't explain is that on a firewall you usually work on two virtual functions. It's not like a switch. Okay, you have like two separate virtual functions. Each function has its own domain and each is configured separately. So with hairpin, what we can do, we can define a special hardware queue and glue it to a TX queue. So when you get packet on one virtual function, you can say, okay, if this, let's say it's a firewall. If I'm matching this is a 5-tuple, it's approved flow, send it to the RX queue. The RX queue is glued to the TX queue. The packet's coming back in the hardware and appearing in the switch. So you have a full accelerated pipeline in hardware. The packet will not go anymore to software. Okay, so now you have a full path in hardware. Packet going from the wire to the firewall, doing hairpin, going back to the switch, and then going to the workload. We need to loop it back. But everything is in hardware. This is already exists, and we also have deployments like this. But this is not like the best we can do. Okay, why it's not the best we can do? Because when you have hairpin, you reschedule the packet. The packet came out of the hardware, and now you put it in a queue. You need to wait for the scheduler to pull it and continue the processing. And then, again, you send it to the VM. It needs to do loopback, and you put it on an RX queue. And again, it should be scheduled and be processed. So we process the packet 3 times. Although the pipeline is the same. Okay. Go from this, from port A to the firewall port A, match city, do a hairpin, send to the port. On the switch, you do the switch logic, like VXLAN decap or whatever, and then you can send it to the VM. The pipeline is the same, but we switch the packet direction 3 times, and this is expensive. Another thing is that we introduce another queue now, and if you have another queue, you now started to compete with the queues of the workload. Each VM has its own queues, and now you need to handle priorities. You want the firewall not to block the VM, so it should be higher priority, and it started to get complicated. Okay, so what we can do? So we want to avoid packet direction changes. So the first thing that we need to do, we need not to write it in the code. Okay, in RT flow, it was called ingress and egress, but it's TX and RX. You put a table explicitly on one of the directions. So there is no way someone can optimize a thing like that if you tell the hardware, put it here, do helping, and put it there. So we need to get rid of those directions in order to do some optimization. Because if you look in a high level, the direction should be maintained. You have RX to the VM, so it's a pipeline. Switch, firewall, switch, workload, and the other way around. And they're all on the same direction. Okay, so we need to get rid of this RxTX. So what we're going to do, we're going to have what is called local or unified FDB. On the firewall itself, we're going to take all those virtual functions. It's usually 2, but it could be 4 or 8 or how much the customer wants. And we merge them into a switch. Now a packet coming to the virtual function, the first thing it's going to hit is the switch. Like it's an exact copy of the switch below. Packet from each of the uplinks or the VMs or the virtual functions hit the same place. It's the root table of the switch. And from that, you can match from each port you came, and you can do all the processing. You have no longer a direction like egress or ingress. And of course, the RX and TX, those are maintained. If from the switch itself you want to send to the VAF, you still can use RX and TX and Airplane and all of this. Okay, so what we did is we removed the need for a direction. We're working like a switch now. Okay, now how this helps to optimize? Because there is no direction anymore, it's just a switch. When in the switch, a packet came, let's say from port A, the first port, let's call it port A, and I'm telling, I want send it please to port B. Internally, since it's a configuration I did, and I know it's an STD switch on the chip, I can jump directly to the hypervisor switch. I don't need to go through helping queue anymore. I'm just jumping to the switch. Okay. So this is the pipeline. Each color can be implemented by a different company. Okay, the switch can be OVS, open source community. The green firewall of some company, I don't know, Check, Palo Alto, Cisco, whatever. And the workload can be whatever the customer wants. And they don't know about each other. Okay? So you write, you just need now an orchestration that will tell you to do this local FDB on the firewall. And from that point, everything is transparent and without any additional coding of the user. So let's go through this. Packet coming from the wire, okay? First, hit the switch, the hypervisor switch. The hypervisor switch has a rule that tells it, okay, go to the firewall, okay? The firewall that was written by another company and used running on a VM or container, we're using RT flow to configure the hardware acceleration, okay? If it's a firewall, let's say the first few packets we go to software and then you approve or deny the flow. You configure the connection tracking table you have and you say either drop or send to the other port. When you send to the other port, because this is a local FDB, it's like a second hierarchy, internally, you can jump directly to the FDB. You don't need to move through the scheduler. It's still one-time schedule. Again, the packet will hit the switch, this time from a different port. The switch can do the switch logic, and then send it to the right VM. So we maintain the direction, the entire direction, without flipping the packets anymore. We also made it like modular, that each component can be written separately and by different company, and the only one that should know about it is the orchestration that need to put this local FDB together. Okay, on the TX side, this is the same. Okay, the workload is sending packets to the hypervisor. The hypervisor, the switch will do the switching part, then we send to the firewall. If the firewall approves this packet, it will send it to the wire. No need to change the packets, okay? Now, there's still limitation on that, because each hardware has its own limitation. For example, if you want to encrypt or decrypt, in this case, if you're sending packet from the, I'm talking about here on NVIDIA explicitly, if you're sending packet from the VM, and you are on the TX side, we cannot decrypt. But it also doesn't make sense that the VM will send encrypted packet and you want to decrypt it on the switch. It's always the other way around. And there might be some other limitations, but we work on, this is the only limitation I know about, but we are working on removing them and eliminating the need for direction completely. Okay, now, this was about firewall, but if we think about it, there are VNF that you want to combine few VNF together. You have, like in 5G, you have what is called UPF that can be virtualized, and some of it can be sent to a gateway which can be virtualized. And this topology can work also for let's call it microservice architecture, that you have few services, each one is accelerated. The only thing that you need is to do this local FDB inside, and you need a switch that can direct the packets. Okay, so this is a result. Okay, we did more or less the same. We just eliminated the 2 points of the loopback and hairpin, and this makes the hardware work much better because you schedule the packet once. It's a one-direction runtime. It's more easy to let's say predict performance, less jitter, less latency, work better. And there's the full separation between the workloads. Everything is separated. There is no, I don't know, you don't offload functionality from one side to another. You don't, if you want to encrypt or do firewall, you don't start to add functionality to the switch. You just put a firewall and that's it. So such an architecture can give vendors ability to write their own service with full acceleration, and knowing they can be run as a service in such a topology. Switch, if you look on a VNF, I think I skipped that, but on a single appliance, we also do the hairpin stuff, okay? You have, like, if you take the entire box for doing firewall, you still want to do wire for wire, it works with hairpin, and this is what we do today. But if customers will work on a switch, in this case, it will be, for them, it will be the same. You just send from port to port. You just need to put explicitly the hairpin. So they can write the application once with one offload without knowing if they will run as a standalone on the entire box or run as a service. Okay, so our hardware pipeline is end-to-end. There is no changing in direction, which means the best latency, the minimal scheduling effort, and the best performance. As I said, firewall is just an example for that. There are other things that could be done: load balancer, encryption, gateway. They're doing NAT, and others, and also in more complicated scenarios, not CSPs that run in cloud, like let's say 5G network. There are multiple VNF that can be run on the same host, and it can communicate with them and get the best performance from the hardware. That's it. Questions?
Thank you for the presentation. Something I don't understand. What you presented is something that is already available, or is it something that...
We are pushing it upstream. It requires also kernel, because you need to merge virtual functions together. We are pushing it upstream. It will be in the next year, I believe.
Okay, thank you.
Is there any dependency on a type of NIC, like CX6, CX7, or support will be generic?
From ConnectX 6, we can support it. It depends on hardware steering.
Sorry, can you please reiterate on the point what's the main change between the loopback solution and the new variant?
Yeah. This is like a bit of a history, because when you have like appliance, like a firewall, you're bumping the wire. You get a packet from one side, public and private, and you send to the other side. And the solution for that, and you're running on 2 ports, virtual functions, usually, okay? And the solution for that with RT flow is putting rules on ingress or egress and moving using helping, which was a revolution back 6 years ago, from side to side. But when you're doing that, it means that you reschedule the packet. Okay, you got out of the hardware on the RX, and now you schedule TX. It's similar like someone send a packet from one of the virtual functions. And this costs performance. Now, if you're doing it as a standalone, you're bumping the wire, there is no cost, because this is the best the hardware can do. But if you are not alone on the host, there are others, like a switch, you're now starting to flip the packet back and forth per direction. Because once you did the helping and you're going back to the switch, you want to send it to the workload. Now you're in the direction of going out to the wire. So you need, we do it internally, okay, it's loop back, but you flip the packet again and you reschedule it. So now you have 3 packets instead of 1 from a hardware perspective. And in order to get rid of that, first you need to get rid of the syntax of the terminology. You cannot put this on the egress and put this on the ingress and do helping, because we cannot optimize. We will do what you want. Instead of that, you work also or switch. You are no longer, let's take the simple use case, you have 2 virtual functions. Instead of now offloading a rule to ingress, egress, you merge them together into a switch, and you put only rules on the switch, where there are only ingress in switch, one direction, okay? And then, internally, we can do those jumps. Okay, when you send a packet down to the switch, you don't need to do helping. We just internally, we switch domain and jump to the root table of the switch. Okay?
Okay, thank you.
Sorry, can you explain that again? It's not going to the firewall? A switch does the firewall functionality? I did not get that part.
I can't hear.
Questions over there too. You all set?
I didn't hear the question, sorry.
Okay.
Can you hear me now?
Yeah, but...
Yeah. So can you explain that again, what you were explaining? When it goes to the switch, how does it go back to the firewall for firewall functionality?
You mean this slide?
No, the next slide, right? The next slide. Next. Yeah, here.
Here,
Yes.
you're working on a switch. If you're working on a switch, there is no direction. Everything is egress, I think, or ingress, one of them. Egress? Okay. There is no like a direction of domains. Okay, there is one. So you don't need any more to also create helping queues, because when in a switch, when you tell, let's go with uplinks. If you got from one uplink and you want to go to the second uplink, you don't need to do anything specifically. Okay, we just send it to the wire. And this is not like virtual functions when you must use helping.
Hi. With your solution, are you able to minimize the DMA bandwidth or the PCI bandwidth?
You don't have PCI bandwidth. You also reduce the PCI.
So the VNFs are the workload VNF and the firewall VNF are on the host. So it must be going through the PCI, right?
No, the packet is in hardware. Only PCI bandwidth that you need is if you have like big tables and you need to have memory, you have cache misses, you need to bring memory. So it's everything. It's one hardware. Just you have isolation. You have what we call Gavami. You have a domain of isolation that you can jump between them. It's not going through the PCI.
So the packet is being delivered to all the VNF sites. So in the service function chaining, if there are 3 VNFs are there, you are going to deliver the packet to all the 3 virtual functions, right? So some penalty is happening, right, somewhere, either the DMA or the PCI.
Now, PCI is only when you send packet to software, and in this case, it will be the last one, right? The workload. In this case, where it is, yeah, the workload. Only on the workload, it will go through the PCI. We also use PCI to bring memory. If you have like a very large amount of rows in the hardware and it doesn't fit in the NIC cache, then we have cache miss and then you use the PCI to get the memory. Okay, but the packet on the PCI only goes to the workload in this case, and that's it, and from the workload.
Okay.
Thank you.